Good day, everyone. My name is Alexander Berezovsky. Together with my co-author, Professor Grigori Zheltkevich from Ivan-Franko National University of Lviv, I will present our work on Lamport spacetime diagrams and logical clocks. The topic is event ordering and causality in distributed systems, with applications to distributed ledger technology. Modern data systems are moving away from centralized cloud providers. A central system depends on one trusted company, which creates three risks: a single point of failure, the power to censor or change data, and an unfair balance of power between operator and user. For public records, such as identity data, medical records, patents, this is just not acceptable. Distributed ledger technology, or DLT, offers a different model. Trust no longer depends on one company. Instead, it depends on cryptography and on agreement between independent nodes. The ledger becomes hard to break, easy to check, and cannot be changed after the fact. But DLT raises one basic question. With no central authority and no shared clock, how can nodes agree on the order of events? This is the starting point of our paper. A natural idea is to use physical time, say UTC timestamps. Unfortunately, this fails for two reasons. First, clocks on different nodes drift apart. A few milliseconds of difference is enough to put transactions in the wrong order, not acceptable in a ledger. Second, physical time tells us nothing about cause and effect. Message A can be sent before message B, but if A is slow on the network, it may arrive with a later timestamp. Cause can look like it happened after the effect. What we need is logical time, time that comes from the cause and effect structure of the event themselves. This idea was introduced by Leslie Lamport in his 1978 paper. Lamport's algorithm is simple, with three rules. First, each node keeps a counter and adds one every time a local event happens. Second, when the node sends a message, it attaches the current counter value. Third, when the node receives a message, it takes the larger of its counter and the received one, and adds one. This gives the key property. If event A causes event B, the logical time of A is smaller than the logical time of B. However, the classical Lamport clock has two problems. First, two parallel events with no cause and effect link, can end up with the same timestamp. The timestamp cannot serve as a unique name. In a ledger, every transaction must be uniquely named, so this is a serious issue. Earlier work fixed it by skipping numbers, but that creates gaps in the sequence. So our research questions are: can we build logical clocks where different events always get different timestamps, and the timestamps form a full sequence without gaps? To answer this, we first need a formal model of Lamport diagram. To reason about distributed runs, Lamport introduced the spacetime diagram. The picture is easy to read. Each vertical line is one node, one sequential thread of work. Each dot on this line is an event. The dot's position tells us the order of events inside the node. Events come in three kinds. A local event labeled DO is a computation on one node. A send event dispatches a message. A receive event accepts a message from another node. The arrows show two relationships. Vertical arrows connect consecutive events on the same node. Horizontal arrows connect a send to its match and receive, one arrow per message. That is all we need to reason about cause and effect in a distributed system. Now the formal model. A Lamport diagram is a triple: P, E, and trigger. P is the set of process identifiers, a finite, non-empty set of natural numbers. Each number names one node. E is a set of events. Each event is a pair, a node identifier and a local event number. We write E sub n with a small p on top for the nth event of node P. Every event carries an attribute called act, with one of three values: do, send, receive. The third part, trigger, is a function. For every receive, it points to the match and send. This formally links message reception to dispatch. Compared to earlier work, we add one idea. We treat act as a frozen. Once an event exists, its kind cannot change. This matches reality at every moment and knows what it's doing. This small change makes several later proofs simpler. For a triple to be a valid Lamport diagram, we add 6 conditions, L1 through L6. L1 says there is at least one node. L2 says no gaps in the local sequence. If event number n plus 1 exists, then event number n exists. L3 says that every node has a zeroth event. L4 forbids self-messaging. L5 says no message is received twice. Trigger is one-to-one. L6 is reliability. Every message sent is eventually received. These 6 conditions define what we mean by a Lamport diagram. Everything below is based on them. With the model ready, we can define cause and effect, the happened before relation, written with an arrow. 2 rules. First, consecutive events on the same nodes are ordered, earlier before later. Second, if an event is received, the match and send happens before it. With an extent, if A happens before B and B happens before C, then A happens before C. This gives the full cause and effect order. By construction, the relation is transitive, but it's not automatically free of loops. An event could, in principle, happen before itself. And here is the key observation. A cause and effect loop in a distributed system is a deadlock. Each node is waiting for a message that only appears after the other node has received first. So the absence of loops is exactly what we want, the same as saying the system has no deadlocks. A concrete example. 2 nodes numbered 0 and 1. On each node, the first event is a receive, the next is a send. Trigger is set up so that each node send is the source of the other node's receive. Now follow the cause and effect links. The first event of node 0, a receive, is caused by the send on another node, on node 1. That send is preceded by a receive on node 1. That receive is caused by the send on node 0. And that send is preceded by the very first receive on node 0, where we started. We have a cause and effect loop. An event happened before itself. This is exactly a deadlock. The natural question: how do we systematically check whether a diagram is free of deadlocks? That's where logical clocks come in. Here is the main result. It connects the existence of the logical clock with the absence of deadlocks. A logical clock is a function C that assigns a time value to each event from an ordered set that behaves like the natural numbers. The required property: whenever one event happens before another, the first time value is strictly smaller. The clock respects cause and effect. Easy direction: if such a clock exists, happened before, has no loops. Otherwise, some time value would be smaller than itself. Hard direction: our main theorem. Whenever happened before has no loops, a logical clock into the natural number exists. We built it explicitly. For each event, we construct a tree of everything it depends on, and the clock value is the tree's height. The proof uses a counting argument. If the tree were infinite, some node identifier would appear infinitely often. Taking 2 repeats gives a cause and effect loop contradiction. So the tree is finite and the clock is well defined. Putting both directions together, a diagram has no deadlocks if and only if a logical clock exists on it. The Lamport clock we built has a nice extra property. Among all logical clocks of a diagram, it is the smallest one. For any other valid clock C, the Lamport value is always less than or equal to C of E. The smallness has a clean interpretation in category theory. However, smallness comes with a limitation. Consider 2 nodes exchanging messages back and forth in lockstep. When we compute the Lamport clock, corresponding events on the 2 nodes get exactly the same value. For every n on node 0 and event n on node 1 both receive the value n. So the classical Lamport clock orders events correctly and detects deadlocks correctly, but it cannot give each event a unique name. In a ledger, where every transaction must be uniquely addressable, this is not acceptable. That brings us to our final contribution. Our fix combines the Lamport clock with a wave algorithm, building on earlier work. Instead of mapping events to plain numbers, we map each event to a pair, a logical time and a node identifier. We compare pairs in dictionary order. Times first, then node identifiers as the tiebreakers. This new scale is still well-ordered and still behaves like the natural number, so nothing breaks in the definition of a logical clock. Our first result, the modified Lamport clock, is both a valid local clock and a one-to-one function. No two events share the same value. Proof sketch. Projection onto the first component recovers the classical Lamport clock, so cause and effect is respected. For one-to-one, if two events have the same Lamport value, they must be parallel events. Parallel events live on different nodes, so their node identifiers differs, and the pairs differs. We now have a clock that orders correctly, is still minimal in its first component, and gives every event a unique name, exactly what a distributed ledger needs. To summarize, first, we built a formal model of Lamport diagrams with 6 conditions L1 through L6. Second, we formalized cause and effect with the happened before relation, and proved that existence of a logical clock is exactly the absence of cause and effect loops, the absence of deadlocks. Third, we showed that the classical Lamport clock is the smallest logical clock for any diagram, with a clean interpretation in category theory. Fourth, we identified its main weakness, non-uniqueness, and proved that a modified algorithm combining Lamport with a wave gives every event a unique value. The practical impact. Logical time can serve not only as an order, but as a unique identifier for every transaction in a distributed ledger. This directly improves data consistency, integrity, and reliability. Future work goes in 2 directions. First, a more general version of the language of category theory. Second, an engineering implementation inside a working distributed ledger prototype. Thank you very much for your attention.